So welcome to this part of the previous lecture. So in this lecture we will continue from where we have left in the last slide. So in the last slide we discussed about our mod 6 counter. So here we will start with mod 10 counter. So our mod 10 counter, so is as the name suggests, in the previous case we have counted the mod 6 counter was the counter which counts 6 number of counts, okay, 0 to 5. So mod 10 counter have 10 states, okay. The other name for the mod counter for mod 10 counter is also decade counter. So decade means 10, so it have 10 counts. So the 10 counts starting from the 0, the counter can count up to 9, so 0 to 9. So in all there are 10 counts. So now if you want to count up to 10, then the number of flip-flops required to design a mod 10 asynchronous counters will be satisfying this criteria. If you satisfy this, if you keep this criteria in mind, so n is your 10, and if you determine the value of this small n, then it will, to fulfill this criteria, this small n should be equal to 4. So that is why you require 4 number of flip-flops. And again we use the same arrangement, same T flip-flop to design the circuit, so that we will see later on. But if we use 4 flip-flops, then the possible number of states which it can count can be 16. So 16 number of possible states. Among them, the 10 are the valid states, so that is what we want, whereas the remaining 6 are the invalid states. So as you know from our previous discussion that for the invalid states we make the counter, for the first invalid state we first bring it to the 0 state, okay, reset it, and then later on we don't care for the remaining states. So we will use that particular thing and we'll draw the truth table, timing diagram, and the logic circuit keeping this in mind. So the stable states are from the first 10 states are the stable states, right from 000 to 1001, that is the 9. Okay, so these are the initial counter initial counter states, and when the counter goes to the next state 1010, okay, after the 9th clock pulse the counter resets to 0000 again. Okay, so after the 9th clock pulse it goes to 1001, and then at the 10th clock pulse it goes, after the 10th clock pulse, after the 9th clock pulse, at the starting of the 10th clock pulse it temporarily goes to 100, and then when it goes to 1010 for a temporary state for time being, then it resets to 000 again. Okay, and then the counting again starts from 00. So that is why it is called mod 10 counter. So whatever we have discussed here, the same thing is written in this truth table also. So when this clock pulses occur, so after the 0th clock pulse this counter have this state. So Q1, Q2, because there are 4 counters, 4 flip-flops we are using, so this is the LSB counter, this is the LSB flip-flop Q1, whereas the Q4 is our MSB flip-flop. Okay, so Q1 to Q4. So for after 0th clock pulse this should be the state, after first clock pulse this should be the state, similarly second this, third this, fourth this, and after the 9th clock pulse the state should be this. Okay, and at the 10th, after the 10th clock pulse it should again come to 000 state. Okay, so to do this, for this particular case it should generate to the reset. Okay, I have not I forgot to write this reset table here, but this reset should become 1 in this case. Okay, whereas for the other cases, okay, so for this 1010 case, when the state goes to for the after 1001 the counter will go in the state 1010 for it will temporarily go into the state 1010. Okay, so when it goes into the state 1010 the counter should get reset. So if you assume that there is an this reset terminal also here, then that reset terminal will be 0 for all these cases, but it will become 1 for the temporary case when the counter goes to 1010 state. Okay, so temporarily when the counter goes to 1010 state, that reset, which I am asking you to assume it here, will become 1 in that particular case, and after that it will be don't care. Okay, so after that it will, you should treat it as don't care, because you see whatever it is, like 1 or 0, it should not affect your count. Okay, so that is why you are considering it as don't care. So we fill it up all this in our K-map. So we make a K-map for our reset, this reset terminal, reset terminal, and this reset terminal, if you write for the reset terminal, if you write the this k-map, then our k-map entries becomes 1 for the 6 invalid states. So 3 and this 1 2 3 4 and this remaining states. Okay, so 5 6 are the invalid state. So this 6 for the 6 invalid states, the counter becomes 1, becomes don't care, whereas for this state it will be 1. Okay, so for this 10th it will be 1. Okay, now for the remaining 11 12 13 14 15, it will be 1 1 1. Okay, it will be don't care. So if we fill this all up here, then our counter will become this. If we see this, okay, so this should not be there. Okay, so there is a mistake in this, so you should assume this cross is not present there. Okay, this is 0. Now if this entries we make, so considering this, if you design a mod 10 asynchronous counter, so you know that we have used 4 flip-flops. So this 4 flip-flops are used in this manner. Okay, so 4 flip-flops. Again, the output of the first flip-flop becomes the input to the clock of the second flip-flop, and similarly for the others. So the output of the second becomes the input to the flip-flop of the becomes the clock input to the third flip-flop. Okay, and similarly for the fourth. Now there is a clear input which is like connected together with the reset. Okay, this we already have understood. Then these are T flip-flops, so T is connected to 1 permanently, T input is connected to 1 permanently. Okay, and these are the Q1, Q2, Q3, Q4 outputs. Now this reset signal will be generated. How this reset signal will be generated? Because this reset signal should be connected to the clear input, because the flip-flops should be reset, should get reset for this temporary count 1010. So we have to make this arrangement. We have to use some combinational circuit here. So this combinational circuit can be designed with the help of this this k-map. So if we have made these entries, as I have already explained you, that these entries, if you simplify it, then your reset terminal will get the value as Q4 Q2. Okay, and as this is you want to generate, let's say R bar, reset bar, then you will use a NOT gate. If you like to generate suppose reset only, then you will use a AND gate here. But if you are generating R bar, okay, reset bar, because this is our clear bars. Okay, so this is bubbles we are using here, that is why. So this NAND, if you want to generate reset bar, then we will use a NAND gate here, and we connect a NAND gate to these two inputs, Q4 and Q2. So Q4 and Q2, this becomes the two inputs to this NAND gate, and the output is connected to this clear, okay, in a clear terminal. So this is how you generate your mod 10 counter, and you can verify its operation with the help of this timing diagram. So what does this timing diagram says? This timing diagram says that when your negative edges, because this is a negative edge triggered flip-flop, if you look the circuit, then you can see that it is a negative edge triggered flip-flop. Okay, so the bubbles are there and the edges are there, triangle are there. So the triangle shows that it is a edge triggered, and the bubbles shows that it is a negative edge. So you see, when the first negative edge of the clock pulse appears, then Q1 transits. Okay, so if Q1 is 0 initially, then it becomes 1. So initially we assume that the counter is resetted and all the counts are at 0 0 0. So at the first clock pulse, first negative clock edge, the Q1 transits to 1. Then on the second negative edge, it transits to 0, and so on and so forth. So Q1 changes, then when the negative edge of the Q1 occurs, then Q2 transits. Okay, so when this negative edge of Q2 occurs, then Q3 transits, and when the negative edge of Q3 occurs, then Q4 transits. So now if this happens, then we can see that our clear bar remains 1, and this becomes 0, or the circuit gets resetted only for this temporary state. Okay, so when this temporary state happens, so in this case only the counters gets resetted. Okay, so let's see if this happens, then our counter remains in which state. So initially if it is in 0 0 0 state, then this is our MSB and this is our LSB. So Q4 is our MSB and Q1 is our LSB. So the counter goes into the next state is 0 0 1, 0 0 0 1, then it goes into 0 0 1 0, then it goes into 0 0 1 1, then it goes to 0 0 0 0, then it goes into 0 1 0 1, okay, 0 1 0 1, then it goes into 0 1 1 0, then it goes into 0 1 1 1, then it goes into 1000, then it goes into 1001. So you can see that it is going starting from the 00 up to 1001. So all the 10 states, the counter is going from into all the 10 states, and as soon as this states occur 1010, okay, so what happens, the transistor, this counter gets resetted because we have made this arrangement. We have returned the scheme map for the reset signal, and we have also sorry, what happened? So let me return back to that slide. So you see, so we have seen that we have generated this reset signal, okay, according to our the signal. So the circuit gets resetted when this 1010 arrangement occurs. Okay, so that is why it is resetting, and our circuit gets resetted to the 00 again. And when the next clock pulse occurs, circuit will again start counting from the 000 state. Okay, so this is how your mod 10 counter, asynchronous counters looks like. So with this you understand that how to design asynchronous counters, and not only asynchronous, general asynchronous counters, but any mod n asynchronous counters. So you can generate mod n asynchronous counters in this way. So I've given you two examples, and considering this you can now design any circuit. If you have any problem, you can clarify it in the tutorial class. Okay, so ask me in that. So now let's discuss about the disadvantages of asynchronous counter. I have already told you that they are they have two problems. Okay, so basically they are slow. Okay, and this is because of they are slow, but they are easy to design. So easy to design because the arrangement, we know that how to connect this circuit and how to draw this reset circuit also. So that is very simple, not difficult at all. But these circuits have a certain problem, that they are slow, and these synchronous counters are slow because they have this can become too slow because sometimes the propagation delay, okay, is too large. So the propagation delay of these counters, okay, asynchronous counters are not useful. These asynchronous counters are not useful at very high frequencies. Okay, because because when the number of bits are because if the number of bits are very high, if you are using it for small number of bits, let's say 2 bits, 3 bits, then okay, then the propagation delay will not be too much. But if you are designing the circuit for let's say 8-bit or 10-bit circuit, then there will be too many flip-flops, okay, 10 flip-flops, and it can go up to 2 to the power 10 or 2 to the power 8 states, okay, accordingly. So in that case, the propagation delay means the delay when you apply the time span, the time expand when you apply the input, and corresponding to that input how much time it takes to generate the output, because as soon as you apply the input, the output will not change instantaneously. It will take some time. The time taken will be dependent upon how many number of gates you are using in between to process that circuit, to process that signal. Okay, so if the number of if you increase the number of logic gates, okay, if you increase the number of counters, if you increase the number of flip-flops, not the counters, if you increase the number of bits, then what happens, the in between gates will be too many. Okay, the number of gates to realize this, in the next unit we will see that how to realize this gates. Okay, so inside the gates there will be some transistors. So those transistors will always have some propagation delay, some time delay. The delay or the time which spends, okay, so the time which passes during the time when you apply the input, and for that input the output also changes, so that time is called the propagation delay. So the propagation delay becomes an important issue in case of asynchronous counters. Okay, then the second issue with the asynchronous counters is that they generate some temporary incorrect arrangements, and for those incorrect arrangements, that what happens, some glitches are also generated. Okay, so there are two problems, propagation delay and the glitches in the asynchronous counter. So we'll understand this propagation delay and glitches, okay, and how to do this. So disadvantages of propagation delay. So propagation delay you can see with this in this particular waveform. So if the number of clock pulses are there, and if the number of flip-flops are too many, then what will happen, let's say with we'll try to understand with three outputs only. So Q0 is our LSB, and Q2 is our LSB in this case. So when this first clock pulse appears, okay, so when the first transition occurs, then this Q0 is changing because you see this is, let's say, positive age triggered. So when this clock transits, after some time Q0 transits. In the previous cases we have assumed that the transition occurs at the same instant. Why? Because we have assumed ideal conditions, but practically if you consider, then there will be always some delay. Okay, after that the circuit will start responding. Okay, so you see, when the input changes, after some time the output starts responding because of the propagation delay. Okay, because we are considering the actual scenario here. So when this happens, let's say if you are using only one flip-flop, then the delay will be less. But if you are using two flip-flops, because this is the output at the after the second flip-flop, then what will happen? You see the delay is increased, because if it was let's say 10 nanoseconds in this case, then again if you are using the same flip-flop, then again for the second flip-flop it is 10 nanosecond again. So then you see the total delay will be 20 nanoseconds. Okay, so the Q2 or the second flip-flop output will change after 20 nanoseconds after the clock pulse changes. Okay, so that is what it means. Similarly, if you are using, let's say, third flip-flop, so the time delay will be 60 nanoseconds, okay, or 30 nanoseconds. So if it is 10 nanoseconds for each flip-flop, so 10, 20 and 30 nanoseconds will become. So you see, if you are using a clock pulse here, and if the clock pulse itself have, let's say, this on period of, let's say, 25 nanoseconds. So and if you are using three flip-flops, so then the propagation delay will happen what? The propagation delay, because of this propagation delay, although the clock will again settle to 0, but the output will start changing after that, because the time duration for which the clock pulse will remain high will be 25 nanoseconds, but the output will become high only after that. And sometimes the duration is so large that it may skip some stages as well. Okay, it may skip some counts as well. Because of that, this circuits may have problems as well. Okay, so the delay will be too large. So this is an issue, okay, which should be taken into consideration while designing the asynchronous counters. So when you design asynchronous counters, this asynchronous counters, as I have told you, are already, they are simple to design, but they have this sort of problem of propagation delay. Okay, so we should be aware of that, how many number of stages we are using, or how many number of bits we are using to design these asynchronous counters. So these asynchronous counters, if are designed for too many number of bits, then there will be always a problem of propagation delay in this case, in these circuits. Okay. Then there is another problem, which is, and you should you should always be take care of this particular thing, that the maximum cumulative delay in the counter must be less than the period of the clock waveform, because in that, if this happens, then your counter may skip some stages. Okay. Then the another problem is glitches. So what happens? Glitches are nothing but if you understand the glitches, then these are the erroneous output or the wrong output patterns which generates, okay, when your circuit transits. Okay, so if your circuit is transiting, let's say if you have some arrangements, and if it is transiting from, let's say, if you consider this clock pulse, okay, if this timing diagram, so if your circuit is, let's say, in the initial state 0 0 0, and it transits to some counts. So first it is 0 0 1, 0 0 0, then it is coming to 0 0 1, then it should come into the next state as 0 1 0. But here you see that the counter is remaining because of the propagation delay. Okay, some glitch occurs. So for this duration, the count remains 0 1 0 only. Okay, although the count should change to 0 1 1 0 1 0, but it remains 0 0 0. Okay, so it is becoming 0 0 0 in this region. You can see this. Okay, so it is becoming 0 0 in this region. So this incorrect output in this certain state, okay, is called your glitch. So whenever this propagation delay is too large, then the glitch's size will also be too large, and you may then interpret the output as incorrect, because in between it is always show some incorrect outputs. So they are called glitches, and that should be avoided. In case of asynchronous counters, if the number of flip-flops are too many, then there will be problem of these glitches. Okay, so we should be very careful about this as well. So I've explained you what the glitches are and how they are harmful to us. Okay, then let's say let's try to, because I have talked about the propagation delay, so let us try to calculate propagation delay for some circuits. So propagation delay for, let's say, a simple circuit we have. So okay, there is some problem in this. I have corrected it, but it is not showing here. So I'll show you in the next the slide. So let me change it. So you see, this is where we are. So we have an asynchronous mod counter. So we want to calculate the propagation delay for this circuit. So how to calculate a propagation delay for this circuit? So let's say the question is something like this. You have a 4-bit counter, and in this counter, each flip-flop has a propagation delay of 10 nanoseconds. So we want the total propagation delay, determine the total propagation delay from the triggering age of the clock pulse until a corresponding change can occur in the state of the last flip-flop. So you have this 4 flip-flops, right from Q0 to Q3, Q0, Q1, Q2, Q3. There are 4 flip-flops. So each flip-flop have the propagation delay of 10 nanoseconds. So you want that what will be the total propagation delay after the 4th flip-flop. So it is very simple to calculate. If each flip-flop have the this delay of 10 nanoseconds, propagation delay of 10 nanoseconds, then you can easily say that the propagation delay of the total propagation delay, the cumulative propagation delay after the 4th flip-flop will be 4 into 10 nanoseconds. So it is very simple, so which is 40 nanosecond. But then the second part of the question says that also determine the maximum clock frequency at which the counter can be operated. So the question is asking that what should be the maximum clock frequency which we can apply. Okay, so what should be the maximum clock frequency which can be applied to the input of the first flip-flop. So to determine that, what we have to do is we have to take this into consideration, this propagation delay. Okay, so the cumulative propagation delay we have to be careful about. So the maximum clock frequency will depend upon this propagation delay, the cumulative propagation delay. So if your cumulative propagation delay here in this case is 40 nanosecond, then you know that the frequency is obviously inverse of the time period. So the maximum frequency will be nothing but the 1 upon this total cumulative propagation delay or the total propagation delay. So here in this case you will find the maximum frequency which you can apply to the circuit is only 25 megahertz. So you cannot operate the circuit beyond 25 megahertz. Okay, so this is how you determine. And this probably you may recall it that in the processors also you see that in the microprocessors which you use for your computers or for your mobiles, okay, nowadays, so you may see that it have certain maximum frequency limit. Okay, so that comes from here only. Okay, so that is one of the reason you can understand that the propagation delay for those circuits is such that those circuit can be operated at 1 gigahertz or 1.2 gigahertz, something like that. Okay, in nearby in that range. So it is possible that the circuit can be operated only for a certain maximum frequency. It cannot be operated at any frequency, and that frequency of operation depends upon the propagation delay of the circuit. Okay, so my point was this only to explain with the help of this example. Now let's move to the another example. So if an input frequency, the next question says that if an input frequency of 20 kilohertz is applied to a binary ripple counter that has 6 flip-flops. Okay, so what is the output frequency of the last flip-flop? Okay, so the question is, in an input, if an input frequency of 20 kilohertz, so if the clock frequency of the input clock pulse is 200 kilohertz, okay, to a binary ripple counter that has 6 flip-flops. So in all there are 6 flip-flops, and to the first flip-flop we have applied clock pulse which have the frequency of 200 kilohertz. So the question is asking that what will be the frequency at the output of the last flip-flop. So how you will determine it? It is again easy to determine, because I have already explained you that these circuits, these counters can also work as your frequency dividers. Okay, so frequency dividers. So if this circuit is operating initially at 200 kilohertz, then the output flip-flop will obviously operate at lesser frequency. In the previous explanation also you have seen some timing diagrams. So in this circuit also you can see the timing diagram. So if your clock frequency is changing at certain frequency, then the output of the first flip-flop will change at half of the clock frequency. then the output of the second flip-flop, okay, will change again at the half of the first first flip-flop's frequency. Okay, so similarly you can see that the frequency is dividing. Okay, frequency is reducing continuously. As you are moving towards the MSB, the frequency at the output changes. Okay, it reduces by 2, by a factor of 2. So this same thing you can use here to solve this problem. So you see, if your counter is, if an input frequency is 200 kilohertz, so what is the frequency at the output of the sixth flip-flop? So how you will determine it? You will determine the input frequency divided by 2 to the power number of flip-flops. So if it is 6 flip-flops, it 2 to the power 6. So this very simple equation will give you the solution for this. So you see, the answer will be, this solution will give you some answer, so that will be your answer. Okay, so check it whether it is correct or not. So now moving on to the next problem. So this problem says that, and this is the last problem of today's this discussion, asynchronous counters. So this problem says that let's say you have a photocell and a light source combination which is used to generate a signal pulse. Okay, then which is used to generate a signal pulse each time an item crosses its path. So you have certain arrangement and you want to count that how many number of items has crossed that arrangement. Okay, so the counter must be able to count as many number of 1000 items. So how many flip-flops are required to count this? Okay, so you want an asynchronous counter to design this, to count this up to 1000 items. So how you will do it? So again, we know from our previous discussion that the number of counts which the circuit can count, okay, can be 2 to the power with n flip-flops, with a small number, with n is the number of the small n is the number of flip-flops. So with n flip-flops, the counter can count up to a maximum of 2 to the power n minus 1 count. Okay, so the maximum number which up to which it can go is 2 to the power n minus 1. And you want the counter to count up to 1000 items. So what you have to do, you have to equate them together. So you see 2 to the power n minus 1 will be equal to 1000. So now if you solve it, then the number of flip-flops will required to count the item up to 1000 will be 10 flip-flops. So this is how you solve it. Okay, it is very simple, it's not difficult. So you solve it and you find that the number of counts required will be 10. Okay, so with this we complete our asynchronous counter, and we saw all the type of numericals, some type of numericals, and also various type of asynchronous mod counters, and what are the problems which comes in the asynchronous counters and how should be careful about that. So with this we complete this part of the lecture. So thank you for listening. Thank you everyone.